My talk is entitled Finite-difference parquet method and the strong coupling pseudogap. This is work done together with Jem Olim, Dominic Kiese, and Seung-Sook Lee. So as you can see from the title, my talk has sort of two parts, a method part and application part. And so in my motivation, I will also have two parts. First, what do we use this new method for? We use it as a diagrammatic extension of DMFT. So it belongs to the class of methods that aim to describe nonperturbative correlations, including nonlocal ones. And we achieve this by leveraging two established frameworks. On the one hand, we all know DMFT is very successful in describing local correlations. And on the other hand, we have quantum field theory methods, let's say many-body perturbation theory, that we can employ in momentum space in the thermodynamic limit. But here we will be expanding not about the non-interacting limit, but about the local DMFT solution. The particular flavor of DMFT extension we're using is the parquet dynamical vertex approximation, as we've heard before. This is not an easy method, I think that's clear. And I will argue that we gain some numerical advantage by actually considering differences in solutions to the parquet equations. And specifically, this allows us to transform two-particle irreducible vertices, which can be rather nasty objects, into benign full vertices. And I will then illustrate this method with an interesting application, and that's the strong coupling pseudogap. So the 2D Hubard model, of course, needs no introduction in this audience. It has a rich phase diagram. If we are at finite temperature and dope away from half filling, the antiferromagnetic phase soon gives way to the pseudogap phase, which is interesting in and of itself, and also as it borders to the strange metal in the superconducting phases. Now at zero temperature, there are even more interesting phases, and recent work has made some steps toward connecting the pseudogap to the zero temperature phases. But I will not be talking about this. Instead, I will stick to a finite intermediate temperature. Now, to get everybody on board, what is the pseudogap? What do we mean by that? We mean a partial momentum selective suppression of low energy excitations. It's been very well documented in the cuprates, and among the many experimental observables, I here brought some symmetrized ARPIS data. So we will be looking at spectral functions for different momenta on the Fermi surface, starting from the antinode, which is at the edge of the Brion zone, going towards the node in the middle of this quadrant. And you can see that at the antinode, the spectral weight is suppressed at the Fermi level. This curve actually has a minimum at zero energy. And as we go towards the node, this minimum turns into a maximum, and coherent low energy excitations are restored. If this is visualized in a color plot in the first quadrant, the suppressed spectral weight at the antinode then produces these famous fermions. Now the pseudogap has also been well documented in the 2D Hubard model, first by cluster extensions of DMFT. Here I brought plots from this 2010 paper, where the authors used an imaginary time proxy of the spectral weight at the Fermi level for different doping. From the blue data points, we can see that the spectral weight at pi 0, close to the antinode, is suppressed at sufficiently low temperatures. And if the cluster is big enough to also resolve the pi half region close to the node, here we see a much larger spectral weight, so we see this clear nodal-antinodal dichotomy. And then in recent years, diagrammatic Monte Carlo has become the state-of-the-art tool for the pseudogap. The challenge for this method is, of course, resumming the series for large interaction and small temperature, but the strength is a very fine momentum solution, as we can see from these self-energies plotted at selected momenta on the Fermi surface, and also from this spectral function proxy with a fine momentum grid. Both methods have clearly established that the strong coupling pseudogap is driven by short-range antiferromagnetic fluctuations, and I will get back to this later. Here I want to pose the question, well now, We have a third method, diagrammatic extensions of DMFT, including our work. Why do we need another method? What do we add to the picture? Okay, so that's my pitch for the physics. I think with diagrammatic extensions of DMFT, we have very intuitive diagrammatic building blocks, and we can therefore elucidate the important microscopic mechanisms. We can elucidate the role of these building blocks, in particular of the magnetic Hedin vertex. This has been done before and by us, however, with important differences. So what is the role of the Hedin vertex? Let's start from the weak coupling pseudogap. Right? We know there we have very long range spin fluctuations, and electrons scatter off these spin fluctuations. That's all we need. In conventional spin fluctuation theory, we take the simplest diagram where the wiggly line is the magnetic susceptibility, which is very sharply peaked at pi pi. And that's all we need. We close this with a bare propagator, and we get the appropriate momentum-dependent self-energy. Now, as we go to the strong coupling pseudogap, the spin fluctuations are much less pronounced. They're much shorter ranged. So how can they still manage to open a pseudogap? They can do that because the electrons already feel these spin fluctuations at a distance. They scatter off of them non-trivially in a non-local, non-instantaneous manner as described by the Hedin vertex. So diagrammatically, this means that this wiggly line here, the magnetic stability, is not the only key player. Now we are at strong coupling, so we need a renormalized propagator and importantly, a renormalized Hedin vertex. And then as we elucidate the role of these diagrammatic building blocks, we can also ask, what are the minimal ingredients? Let's reduce all the non-essentials. And I will argue that what remains, what are the essentials, are local correlations, as we can get them from DMFT, and non-local spin fluctuations that we need to resum in both particle hole channels. So I will get back to this at the end of my talk. And let me now explain the outline for the rest of my talk. I will first explain the method, what is D gamma A, how do 2pi vertex divergences enter. And then I will explain how we can avoid them, and letter D gamma A that's been known, and parquet D gamma A that's new. And I will close this part with a benchmark. And then I will talk about the pseudogap application using results from these three methods. I will discuss the Hedin vertex and arrive at this minimal description I've just mentioned. All right, so how do we go from DMFT to D gamma A in one slide? So this will be a full slide, let me warn you. But okay, so we all know DMFT, it maps a lattice model onto a suitable impurity model. And this suitable impurity model is found in a self-consistency iteration, the underlying approximation being that the self-energy on the lattice is local. It is the self-energy from the impurity model. Let's remember this. And now let's go to our standard quantum field theory knowledge. So here we have self-consistent many-body relations. The first is a beta-zeta equation for the vertex. What does it mean? The vertex has an irreducible building block, and it's complemented by a reducible part that can be obtained iteratively in a ladder summation by concatenating these irreducible building blocks through this pair propagator pi, which is just two Green's functions. Of course, the Green's functions are internally normalized through self-energy obtained from the Schwinger-Dyson equation. All right, so these are exact equations. How to solve them in practice? We need to make some approximation for the irreducible building block. If we take this to be the pair interaction, we get a very simple ladder summation that's basically RPA. Okay, so that's all very well known. Let's take this excursion to a higher level and look at the parquet summation. Here the idea is, why pick this one specific beta-beta equation? There are actually three of them. There are three ways of connecting to 4-point vertices. So we want to solve all of these beta-beta equations simultaneously, include their mutual feedback. This generates reducible contributions in all three channels to the vertex. But this is not everything. There is a sort of remaining fully irreducible part, lambda 2pi. How to solve it in practice? Well, you need to make some approximation for the fully irreducible building block. If you take it as the bare interaction, you get the parquet approximation, PA. All right, so this was the little refresher. And now we come to D gamma A. So I think it's clear that these approximations here, even if for intricate quantities, these are perturbative approximations and therefore will not bring you all the way to strong coupling. And for this reason, it's a very interesting idea to say, let's approximate these irreducible building blocks non-perturbatively. Let's approximate them fully dynamical by the results from the DMFT impurity model. In letter D gamma A, we do this for the 2pi vertex in a given channel, in parquet D gamma A for the fully irreducible vertex. And plugging these ingredients in here, we can solve the equations and ultimately arrive at a momentum-dependent self-energy.
So, Fabian, when you say on the upper right that lambda is of order u and I is of order u, this is just to quote an order of magnitude, right? In reality, what you're going to do is use the full frequency-dependent object.
All right, so what I meant by these approximate signs is that this is a possible approximation, the simplest possible approximation to close the set of equation.
Yeah.
And it is the approximation that gives you RPA or parquet approximation. But if we want to access strong coupling, we should make a better approximation. That is precisely taking fully dynamical vertices from DMFT.
Okay, so you do not do that. Okay.
Now that just sort of is the background. What we do want to do in D gamma A is take non-perturbative input, fully dynamical vertices. And these vertices from the impurity models, they can be obtained with modern impurity solvers, and they have been studied over the years. And then after some time, an interesting observation was made, namely at some sort of innocently looking point in phase space, we can look at the full vertex as a function of fermionic Matsubara frequencies. And it looks perfectly fine, has a magnitude of 8, okay. But the irreducible vertices, they actually have a magnitude going up to 400. So these objects are divergent, have singularities. How can that be? Well, just in a nutshell, the underlying observable is a 4-point correlator. And one gets the full vertex by taking this correlator, subtracting the disconnected part, amputating the legs, nothing can go wrong here. But one gets the irreducible vertices from a matrix inversion. And then it's clear that if this matrix happens to have eigenvalues close to 0, then upon inversion, the irreducible vertices diverge. That's the case for ID, and it's also inherited in lambda 2pi because it differs from this vertex only by some reducible contributions in other channels. All right, so that's the situation that we're facing. We have the D gamma A approximation as a way to go beyond DMFT. There we approximate irreducible vertices to be local, to be taken from the impurity model. However, it's been found these irreducible vertices can be singular, can be very nasty, even in the absence of a phase transition, even if the full vertex is perfectly well behaved. So what does that entail? Does it mean that in these regions of the phase diagram we cannot use D gamma A? Well, actually not. There are ways around, and I want to explain those next. So letter D gamma A, the way around, has been known for a long time. And it goes as follows. So let's write the beta-beta equations on the impurity and on the lattice with lower and uppercase symbols. The idea of letter D gamma A is take the irreducible vertex from the impurity and plug it in here. However, as I just mentioned, this might be dangerous if the irreducible vertex diverges. But we can massage the equations a little bit more before we start computing. Let's first isolate the irreducible vertex for both equations. And then we can simply eliminate this guy by equating both relations. Right? In passing, we generate the difference in pair propagators, and you see that we arrive at this very neat equation, which is the analogon of the lattice beta-peta equation, but the irreducible vertex has been replaced by the full impurity vertex if we just put a little tilde on the pair propagator.
But Fabian, if I can ask, why can you equate them? I mean, the one is for an impurity model, the other one is for a lattice model.
Yes, we can equate them using the assumption, the approximation of letter d gamma A. And letter d gamma A, even if capital IR lives on the lattice, we assume it's purely local.
Okay.
Does not depend on momentum. All right. But I think it's really cute. These are sort of 3 lines, and you see how an irreducible vertex is transformed to a full vertex simply by going to differences, by putting a tilde on the propagator. So this means we can solve our self-consistent equations using only full vertices. 2pi problem completely avoided. And now the obvious question is, can we generalize this to parquet d gamma A? And this question has been open for, I guess, 12 years. So I'm very happy to finally give you the answer on the next slide. Yes, we can also avoid the 2pi vertices in parquet d gamma A. So here we need to solve these 3 coupled beta-peta equations. Let's write them for the reducible vertices again on the impurity and on the lattice. And we also have the parquet equations with these 2pi building blocks. So let's take inspiration from the previous slide and let's work with differences. We're computing the difference in the reducible vertices between lattice and impurity. And by using a sort of discrete analogon of the product rule, you can write this as 3 terms. But so far, this hasn't helped us much because the irreducible vertex still appears. And now it's actually just a few steps to rewrite this in the following way, where suddenly we have full vertices in here. And I want to emphasize these are exact transformations. No approximation has been done so far. We could rewrite the irreducible vertices as full vertices, and this is perfectly analogous to how we derived flow equations a couple of years ago from the parquet equations. But so far, the system of equations is not closed yet, but we can close it by using the parquet d gamma A approximation. And that is, if these 2pi building blocks are the same, this means we can get the full vertex on the lattice from the full vertex of the impurity plus the difference in only reducible contributions. So now again, we have this beautiful comparison that I would like to attract your attention to. This is the parquet equation on the lattice, has a 2-particle irreducible vertex here prominently. We managed to rewrite it by replacing the 2pi vertex with the full vertex of the impurity, and the only thing we need to do is put a tilde on the reducible part. So we've achieved precisely the same thing. We can solve the self-consistent equations without ever using 2pi vertices. We only need the full vertex on the impurity, on the lattice, and the difference in reducible vertices.
So I have another question here, Fabian. Is it obvious that this phi tilde object, which is the difference between 2 objects which do have divergences, that this does not have a divergence?
Yes, this is obvious from the algorithm itself. So you can sort of stare at these equations. Phi tilde is generated from the algorithm, right? You start, it's just a solution of this self-consistent equation. And in this equation, there's no more divergent quantity present. It's only f and some propagators and differences of propagators. So the equations have been transformed in such a way to completely eliminate all divergent impurity quantities, and therefore you will not generate divergences just by solving coupled equations. All right, let's close this part of the talk with a benchmark, and that's for the Hubard model to the Hubard model at half filling and high temperatures. We picked an interaction value that's right at the first vertex divergence of DMFT. So the irreducible vertex of the impurity model diverges, goes up to 10 to the 4, changes sign as we are very close to this u value. But that's not a problem for our algorithm, right? We only need the full vertex. We solve these equations to generate differences in reducible contributions. We can then gather our reducible contributions. And here we see precisely what Jan just asked. The difference in the reducible or irreducible vertex is perfectly well behaved. It has a magnitude of only 0.6, is smooth throughout this divergence point. So yes, indeed, we also see numerically the difference in the reducible vertices does not inherit any singularities. So it works. So if we are agnostic to this 2pi vertex divergences, how good are the results? Well, we can look at the resulting self-energy. Here I'm plotting the difference to DMFT, so only focus on the non-local part. And I'm comparing to determinant quantum Monte Carlo as provided by Yun Yao He. At this high temperature, we can solve the parquet approximation, which is reasonable but not exact. We can solve ladder d gamma A, which gives us a better result. And now we can also solve parquet d gamma A right at this vertex divergence. And we actually get the best results with parquet d gamma A. They're very close to the benchmark. So we're happy that the method not only works, it's not only stable, but also quite accurate, at least at these high temperatures. All right, so that's our method. And now let's... Yeah.
Before you go a little bit further to the physical interpretation, can I ask a question?
Sure.
So I tried the calculation of the parquet d gamma A at u equal to 10 at the same temperature, and I got a convergent result, but which was on the false branch. So it had a very flat self-energy, and the imaginary part was way too metallic. Do you think you could avoid landing on the false branch? Because going a little bit beyond the divergence line does not yet, can not yet prove if you're not going to land on the false branch if you go further. Do you have any reason to believe that you will not end on the false branch?
Yeah, I don't have any sort of experience on how this method performs regarding unphysical branches. I mean, it's the same parquet d gamma A approximation, right? Just the equation is massaged in a way to avoid 2pi divergences. And that's what we focused on here, right? We're solving directly the point where this 2pi vertex diverges, so where you couldn't do it in the default way.
Yes.
As regards to unphysical solution, I think this has to be explored, in particular with the put forward by Alessandro Toschi and Hubard as well, right?
Okay, good.
Okay, let's move on. So let's talk about the strong coupling pseudogap with this method. And we've taken inspiration from this seminal paper by Wei Wu et al., who used this set of parameters, which they identified as having a large onset temperature for the pseudogap. I'm plotting here for you the imaginary part of the Matsubara self-energy, the DMFT result in black, and then diagrammatic Monte Carlo results from this paper. First at the antinode, so that's here at the edge of the Brillouin zone, where we have the strongest imaginary part corresponding to a suppressed spectral weight. Then at the hotspot, which is the intersection of the Fermi surface with this antidiagonal, where the imaginary part is somewhat smaller in magnitude. And finally at the node, which is the intersection of the Fermi surface with the diagonal. And here the imaginary part of the self-energy is much smaller, corresponding to a maximum spectral weight. And actually, we don't only focus on the magnitudes here at the lowest Matsubara frequency, we also focus on the slopes. If the slopes go upward, we call this metallic-like, so the standard scenario. If they go down, this corresponds to a quasi-pole in real frequencies, and we call it insulating-like. I just want to put the parameter values here in some context. Here's a phase diagram from this recent paper by Zimkowitz et al. At a slightly different T prime, but we can see that this U equals 5.6 is in this dark red region, so in the region where the pseudogap is fully formed. It is at fairly large U, I would say, but we actually have another indication for calling it strong coupling physics. Recall that the irreducible vertex on the impurity is obtained by a matrix inversion, and we check for the eigenvalues of this matrix. And as we increase U to 5.6, we actually encounter the fact that the smallest eigenvalue has crossed the origin. So we are very close to a vertex divergence, which I would say is a sign of strong coupling physics indeed. All right, so this is the parameter choice. These are the diag-MC results. Let's try and compute ladder D gamma A for this problem, right? And what we see is maybe a bit of a disappointment. The agreement with diag-MC is very poor, and we do not get a pseudogap behavior. The slope is always upward, so it's positive in this plot throughout the Brion zone. We do not get a strong coupling pseudogap in ladder D gamma A at the Wu point. I want to point out that other papers have documented a strong coupling pseudogap in ladder D gamma A, as shown here. The reason for this discrepancy is probably that these works were at a larger value of U and at lower temperatures. But in any case, we tried all flavors of ladder D gamma A, and we did not find a strong coupling pseudogap at the Wu point. But now, fortunately, we can also solve parquet D gamma A. And lo and behold, here we find much better agreement with diag-MC. The results are consistent, I would say. And we do find a strong coupling pseudogap. We find this qualitative distinction of metallic behavior at the node and progressively insulating behavior at hotspot and antinode. Indeed, from the color plot, you can see that this sort of negative slope really emanates from the antinode here at the edge of the Brion zone. So first of all, we're very happy that we can reproduce this kind of physics, but now we can leverage our method and sort of dissect the ingredients. First of all, we get our self-energy, from a Schwinger-Dyson equation, so it's very natural to perform some kind of fluctuation diagnostics. It's natural to use the parquet decomposition that we have for the full vertex and look at the resulting self-energies. Our vertex is decomposed into a local part, green here, and you can see the local contribution is strong, but metallic and doesn't distinguish between node and antinode. The non-local contributions in the density and singlet channel are flat, are small, negligible, and don't discriminate between the two momentum points either. The pseudogap physics is entirely driven by the non-local part in the magnetic channel, which gives a strong negative insulating-like signal and drives this nodal-antinodal dichotomy. Okay, so here we also reproduce this sort of driving force that was known before, the magnetic fluctuations. Now I found this quite intriguing. If one channel dominates diagrammatically, then why doesn't ladder D gamma A suffice, right? Why do I need to solve 3 coupled beta-beta equations if all the physics takes place in one channel alone? So let's understand what's going on here. What's the difference between the ladder and parquet D gamma A solution? And to this end, we focus on this tilde phi m contribution here and write the single boson part in this Hedin type fashion. So then our ingredients are a Hedin vertex lambda m and the spin sensibility chi m. We look here at the self-energy at the antinode, and again, parquet D gamma A gives the strong insulating signal that produces the pseudogap. Ladder D gamma A does not have this. The result here is very flat and small. All right, let's now play a little game.
Fabian, just to make clear, to be sure, now in this way of analyzing things, the small lambda is still fully frequency dependent, or not?
Yes, it is fully frequency dependent, absolutely. It comes from the self-consistent parquet equations.
Okay, thank you.
But it is frequency dependent in both ladder and parquet D gamma A, but both solutions seem to differ qualitatively, right? So we need to understand something more. Even if they're all frequency dependent, why does one give us the pseudogap and the other does not? Right, let's look at this expression. Let's play a little game. The question here is chi or lambda the key player? All right, let's keep the Hedin vertex from ladder D gamma A and just replace the susceptibility with parquet D gamma A. That doesn't give us anything. We still have this flat and signal and not the strong insulating signal. So apparently it's not chi that takes the lead here. Instead, we might stick with the susceptibility of letter D gamma A, but if we take the Hedin vertex from parquet D gamma A, then we get the strong insulating signal. So this shows that the key player is lambda m. We also plotted this object, and this sort of answers one-to-one's question. It is a frequency-dependent object. He has its dependence on the fermionic Matsubara frequency. You know, the bare value of this object is unity. And interestingly, we find that in parquet D gamma A, the vertex is enhanced. The values are larger than unity. Whereas in DMFT and letter D gamma A, that's basically the typical scenario, they're suppressed. So it really is a qualitatively new feature of parquet D gamma A that the real part of the magnetic Hedin vertex is enhanced. That's how we get the pseudogap in our calculations. We also looked at the imaginary part because this was advocated in the previous work. But at this point, the Wu point, we did not find a strong influence. They look at a different point in parameter space. Good, so now we're one step further. We know that the Hedin vertex is the key player. We might still ask, well, why do we need parquet D gamma A to get this guy correctly if only one channel dominates? And this is explained in this equation. All right.
So you are entering question time. So I suggest you try to wrap up in about 5 minutes.
Yeah, I will do that.
Okay.
All right. So the Hedin vertex has this defining relation. It's irreducible in the boson propagator. That's why we need to subtract the single boson exchange here. Now, again, we insert our decomposition, and you can find that in letter D gamma A, the Hedin vertex is driven by the local vertex F and by the non-local fluctuations in this one channel you select, the magnetic channel, but you subtract the single boson part, and therefore this is a minor contribution. Parquet D gamma A has the other channels as well, and importantly, and that's the key point to all my diagrammatic aficionado friends, the key point is that the magnetic channel also enters in a transversal manner in the opposite particle hole channel. So even if the Hedin vertex is irreducible in the horizontal bosonic propagator, it's still affected by the vertical bosonic propagator. It's still affected by magnetic fluctuations. And that's what's missing in letter D gamma A. That's what drives the pseudogap in parquet D gamma A. We can just confirm this numerically. The main contribution comes from, phi m bar, spin fluctuations in a transversal channel, and mostly so from single boson exchange. This brings me to my final point. What are the minimal essential ingredients? In a minimal manner, the self-energy has this Hedin form. The susceptibility is sort of strongly local and non-local. In letter D gamma A, the Hedin vertex is mostly local. Yeah? We can forget about this multi-boson part. And now in parquet D gamma A, we have the same expression, but additionally, corrections to the Hedin vertex via transversal spin fluctuations. So we can rewrite this as this minimal set of equations. What we need is a Hedin vertex that's sort of jump-started, whose seed is the local result from DMFT, and then self-consistently it's renormalized with non-local spin fluctuations in the transversal particle hole channel. That's all we need. This is what we sort of deduce as the minimal theory. All right, let me conclude. I have 3 points here. First, I showed you our new method, how we can thereby solve parquet D gamma A without encountering 2 pi vertices, how we could reproduce the pseudogap at the Wu point and found that the enhancement of the Hedin vertex is crucial. I want to sort of emphasize this once more. We have 2 anchors, DMFT and parquet. In DMFT alone, we don't get this property. In the parquet approximation alone, we don't get this property of the enhanced Hedin vertex. But if we combine the 2, something beautiful emerges, and we get the strong connecting pseudogap with an enhanced Hedin vertex. The second point is that this Hedin vertex explains why short-range spin fluctuations can open a pseudogap, because the electrons feel that fluctuations at a distance in a non-local, non-instantaneous manner as encoded by the Hedin vertex. And finally, this allows us to derive this minimal set of ingredients needed for the strong coupling pseudogap. And I think this is very interesting because then in qualitative studies, one can use this set of equations to try to solve at lower temperatures, solve for a superconducting instability, and maybe even solve in real frequencies, which is, of course, something that's very dear to my heart. All right. Thank you for the attention. I'm happy to answer questions.
Okay. Thank you very much, Fabian. That was a very nice talk, understanding the strong coupling pseudogap. So there are several questions, but I'm going to start with one which was put in the chat by Markus Wallerberger, who says he doesn't have a microphone, so I'm going to read his question out loud. He says, in principle, the standard version of D gamma A only breaks down exactly at the divergence where the irreducible vertex is ill-defined. So in your analogy, the dragons live only on a set of discrete lines. Did you observe any improvements away from those lines?
So I would say, if we look here, this is not right at the vertex divergence, right? This object is not infinity, but it is 400. So it's up to you if you want to start your self-consistent diagrammatic iteration where you have to deal with cutoffs, with resolution. If you want to start it with an object that's as big as 400, sort of with a natural unit as unity, it's sort of nothing prevents you from trying it. I suspect that it leads to instabilities and hampers the convergence rate. So that's why I believe that the finite difference formulation has an advantage, but I mean, we can try out all possible ways for sure.
Okay, thank you. So the next in line is Carsten.
Hi, Fabian. Great work. You avoided the vertex divergences and rewrote the equations. I have two questions. The first one on the algorithmic side. So taking these differences is not more expensive, right? Or do you need more storage and that is a little bit of a cost, but not too much, I guess? Or how do I have to see that?
Yeah, the storage cost, I would say, is the same. I mean, they are just 4-point vertices. Maybe some differences lead to a slightly quicker decay, but that's not sort of crucial.
But for the differences, you don't need to store object twice or something. You just store the same number of objects, right?
Yes, yeah, we store the same number of objects. Memory-wise, it's the same. I want to point out the computational time. The beta equation now has 4 terms. So in principle, evaluating the right-hand side takes more time because you have to compute 4 summons. So that's sort of the price to pay. You avoid 2 PI objects, but you have to compute more summons on the right-hand side. So that's a balance to choose.
Okay, thanks. And physics-wise, I agree with that you have this extra gamma component that can be important. And with Friedrich Green, we also looked into it for superconductivity. However, from my experience, I think there should be a pseudogap also in D gamma A. So you don't have this mechanism you were talking about, but it then sets still in at somewhat lower temperatures. So my question would be whether you looked at that at all, whether at lower temperatures. So the figure you have here in letter D gamma A, it looks already like it starts to go towards a pseudogap. And of course, if the pseudogap temperature is slightly off, you have big differences. And I agree with that this physical mechanism is important, in particular for small dopings and larger temperatures. But I don't. But I would really think the pseudogap should still open without this mechanism. That's a small lambda.
I fully agree. I fully agree. I mean, I said we didn't find it at the Wu point where I include temperature to be referred at this point. I also agree the hierarchy in incoherence is correct. We go from node hotspot to antinode. And I also think as you go to lower temperature, eventually chi will be strong enough to drive you to the pseudogap. But to actually have this sort of enhancement that extends the pseudogap to a higher temperature via the Hedin vertex, that's the story that we sort of told here.
Thanks.
Okay, so now we have a question by Sasha Lichtenstein.
Okay, Fabian, great. So, look at your great work, but general question. So in principle, your P d gamma A and just d gamma A in principle are the same.
Correct.
Provided that you numerically invert.
It's the same underlying approximation, just the
it's fine.
reshuffling of the equations.
So it's the same. So do I understand? Still, there is some diagram missing. So did you think about relationship with, so you start from DMFT, and there is Rossi method, or good, I don't know who invented RDET, yeah? Renormalized determinant, who start from DMFT and sum up of all diagram. Did you try to compare maybe numerically if you don't understand how it's related? So what diagrams are missing? My question is complicated.
Okay, what diagrams are missing in our approach? Well, this fully irreducible building block is taken to be local, right? And then you can imagine how you take this seed and build all possible diagrams that we solve for self-consistently. But this building block, this seed, we take it to be local. And yeah, I think Anna already also alluded to this, that this will not be sufficient everywhere in the phase diagram. I think at high temperatures, it's a good approximation. At very low temperatures, it will break down.
No, but
yeah.
My question, maybe you already know my question. So even with assumption of local, so you use another assumption solving this Schwinger-Dyson equation. How kosher is this? Yeah, can you prove that even if you start from some correlated model, you still can use this Schwinger-Dyson?
Yeah, the Schwinger-Dyson equation here for the self-energy. Well, it is.
No, but it's you appear. Yeah, you see. So we discuss.
I realize that U appears here, but the equation is what it is, right? It's an exact equation that holds for arbitrarily large U. The fact that the bare U appears in the equation doesn't make it perturbative.
No,
it is
but
an exact relation.
Okay. Maybe I ask carefully. So you use DMFT, and we don't know what is diagrammatic. You mean it's all local diagrams, and I think it's hard to prove that in this approximation you still have something like this equation. So I don't know.
No, the equation holds generally for the Hubard model, so that's fine.
For Hubard model, I have no question. It's exact.
Sure. I mean, to maybe sort of try to find closure. We do an approximate approach, right? And then sort of it's hard to prove how justified it is. The whole spirit of parquet is sort of to exploit these exact relations as much as possible, as they sort of ensure some consistency between the different diagrammatic ingredients. And that's the approach we also follow here, which I think works reasonably well. Of course, you violate other relations, like word identities. It's not phi derivable, etc. So it's as soon as you go approximate, you make some choices, and that's the choice here.
Okay, great. No, but I just ask you maybe if you have RDET results or push some guy from CCQ or just to compare, and then maybe you understand. Because RDET can really, and it's exactly this paper where they calculate V point. In fact, they start, Antoine can prove, they start from DMFT and just do diagrammatic Monte Carlo, which is sum up all diagrams.
Yeah, I agree. I mean, for the benchmarks of
there are a couple of other questions. Anna, you are muted.
Yes, I can speak now. Thank you, Fabian, for an excellent work and very nice talk. I have a question to the transversal particle Hall contributions to the, for example, to the Hedin vertex. They are, however, averaged out over momentum, right? Because you use one form factor. So the Q momentum is averaged. So I believe it's still a not so small contribution, but it's not the same as the contributions in the particle hole channel, or you found a way to take it better into account?
Okay, so yes, we use, I mean, I didn't talk about any computational details. These are heavy computations, as sort of Anna knows best. We use a form factor truncation with just one form factor, so you have to be quite careful in how to still retain some information.
Yes.
Yeah, we talk about it in the supplement. Maybe you can take a look. I don't think we did some revolutionary idea, but we were very careful. And I also think that this strong signal here is washed out in a sense and might be even more prominent if we had a full resolution of all momenta. So it's sort of not the entirely conclusive numerical answer. There are still some details if we could parameterize things better.
Okay, so it is averaged and it still has a lot of influence. That's the only thing I wanted to know. Okay, thank you.
So Fabian, to wrap up things a bit, so can I, from your nice analysis, can I summarize qualitatively things by saying that in the strong coupling regime, the pseudogap comes from coupling to short-range spin fluctuations, which, however, enter the strong coupling regime, where the coupling between the spin fluctuation and the electrons is strong.
Yes, and the strong one might sort of decorate by saying it's non-local and sort of...
Yes, so that was going to be the corollary to my question. So when you say real part of lambda m becomes larger than 1, you refer to what? To the low Matsuba, because lambda m depends on all sorts of things, momenta, frequency, right? So this is...
Yes.
Okay, so this is the low frequency regime at pi pi. Okay, so that answers my question. And what is more important, if that question makes any sense, is it the frequency dependence or the momentum dependence of lambda m? Imagine you have a lambda m which is large, indeed larger than 1, and peaked at pi pi, but somehow completely independent of frequency. Could I phenomenologically reproduce some of the results?
Yeah, we didn't try this out, so one could play even more numerical games. We have some color plots also of this object that shows sort of some peak structure at pi pi. There is some frequency dependence. All of them are, you know, not super strongly peaked, so it's like a mixture of everything. It's hard to say, you know, this one feature is it all. Yeah, one could.
But it would be interesting to sort of try various numerical exercises to abstract a qualitative description. Okay, now I'm running into a problem, which is that there are still 2 more questions, but I personally will have to disconnect because I have to catch a train. So maybe Olivier, can you take over to chair? And the next questions are from Henri Aloul and Friedrich Krien.
Yes, so let's take 2 more questions and then stop because I
have just a small question. Did you try to go towards a higher doping to see whether the pseudogap disappears sharp in the Hubard model?
We only completed this very one point in the phase diagram because sort of it's our new method. We just wanted to showcase it. But I think we could sort of explore the phase diagram and also connect to, you know, the recent paper by Szymkowicz et al. That also mapped out phase diagrams. Yeah.
Okay, that would be nice to see whether the disappearance is fast. So I don't know whether Hubard model will explain that completely.
All right, thanks. And last questions by Friedrich Krien. Hi, Friedrich.
Yes, hello. Can you hear me?
Yes, yes.
Okay, yeah, beautiful. It's a beautiful work. It made me actually skip some work time, so I'm really happy to see that this progresses. I have a question. In our recent paper, we observed that the self energy, that the imaginary part of the self energy on Matsubara scales actually with the vertex. So when you draw them against each other, they fulfill a power law. and that actually allows that superconductivity is still sustained even in a strong pseudogap regime. Do you see a similar connection between the self-energy and the vertex?
We haven't checked for this, no, and I should check out your paper more closely. I could assume that maybe you are at lower temperatures, right? And when you scale, you also mean as a function of temperature? I'm not entirely sure.
Yeah, so you can move in some parameter direction where the pseudogap increases and then the vertex increases as a power law. So basically, it's not really parameter dependent. Like you can just draw gamma against sigma.
Yeah, but we just computed one very point, the Wu point. So we don't have the data sort of to check for such correlations, but it sounds interesting. Yeah, thank you.
Mm-hmm. Okay, thanks.